Hello everyone, this is Nagavi, Assistant Professor from Department of Computer Science. Today we are going to see about the concept image restoration in digital image processing. First let us see what was image restoration. Image restoration, the main objective of the restoration is to improve the quality of the digital image which is degraded because of various factors such as motion blur, improper camera focusing during image acquisition, presence of noise. The restoration techniques focuses on modeling the degradation, applying inverse process in order to recover the original image. Next, a model of the image degradation or restoration process. In the above image, a degradation function exists which together with additive noise operates on the input image f of x, y to produce a degraded image. The objective of restoration is to obtain an estimate f cap of x, y of the original image. If h is linear, then the degraded image is given by the formula g of x, y equals to s star f into x, y plus theta of x, y. The above image represents the input images degraded with a function that is a degradation function h and the additive of noise theta of x, y. This process is called as a degradation. In order to recover the image back to its original, some restoration process is done. For that, some filtering techniques is applied to retain the original image. In the formula given before, star indicates the convolution. In the frequency domain, it is represented as g of u, v equals to h of u, v into f of u, v plus n of u, v. Since convolution in spatial domain equals to multiplication in the frequency domain, correlation is a mathematical operation that is used to measure the similarity between two functions, whereas convolution is a mathematical function which is used to combine two functions to produce a new function. Next, let us see about the motion blur. A motion blur is caused by a relative motion between an image acquisition system and an object during the exposure window. To restore an image that was degraded by motion blur, the motion path must be estimated. For estimating the motion path, we first need to represent a point spread function. Now let us see about the point spread function. The point spread function describes what a single point in the objects look like in the image. Next, the point spread function shows how much of the information in an image spreads into the neighboring areas in the image plane. Next, let us see about the f special function. The f special function creates a two-dimensional filter h of the specified type. Some of the filter types have optional additional parameters. F special returns h as a correlation canal, which is the approximate form to use with the infilter. Next, let us see about the syntax. H is equals to f special of average h size. Returns an averaging filter h of the size h size. Next, h is equal to f special of disk, radius. This returns a circular averaging filter within the square matrix of size 2 into radius plus 1. Next, h is equal to f special of Gaussian, h size, sigma. Returns a rotationally symmetric Gaussian low pass filter of size h size with a standard deviation sigma. Next, the h is equals to f special of Laplacian, alpha. It returns a 3 by 3 filter approximating the shape of two-dimensional Laplacian operator. Alpha controls the shape of the Laplacian. Next, the h is equals to f special of motion, len, theta. This function returns a filter once convolved with an image, the linear motion of a camera. Len specifies the length of the motion, theta specifies the angle of motion in degrees in a counterclockwise direction. By default, the value of length is 9 and the theta value is 0. Next, let us see about infilter function. This function also performs the multidimensional filtering using correlation. When no correlation or convolution option is specified, the infilter by default uses correlation. Infilter performs multidimensional filtering using convolution. The syntax for infilter is infilter of a, h, option 1, option 2. array represents the image, and h is the function that is created using the f special that is passed as the input to the filter function. The options may include one of the following. First, let us see about the boundary options. X input array values outside the bounds of the array are implicitly assumed to have the value x. When no boundary option is specified, the infilter by default uses the x value as 0. Symmetric input array values outside the bounds of the array are computed by mirror reflecting the array across the array border. Next, the circular. This function performs the input array values outside the bounds of the array are computed by implicitly assuming the input array is periodic. Next, output size options. There are two output size options such as same and full. The output array is the same size as the input array. This is the default behavior when no output size options are specified. Next, the full. The output array is a full filtered result and so is larger than the input array. Next, correlation and convolution. CORR. This filter function performs a multidimensional filtering using correlation. Next, the CONV performs a multidimensional filtering function using convolution. Next, let us see about the imnoise function. If the input image is a different class, the imnoise function converts the input image into a double class and then performs the addition of noise with a specified type and the parameters. It usually clips the values between the range of 0 and 1 and then converts the noisy image back to the same class as the input. These are some of the noises which can be added to the image. Here, Gaussian noise, Poisson noise, salt and pepper noise, and speckle noise. For a Gaussian noise, we can specify the 0 mean and the variance value. For a Poisson noise, that is used to generate the artificial noise to the data, and for a salt and pepper noise, we can add a noise density. Next, a speckle noise, that is used to add a multiplicative noise. We can also specify the variance for the speckle noise. Thank you for watching.